Hi, and welcome to what is it, week 4 for in the fall of 2020 for Physics 4B. Again, as I was talking about, we're going to finish chapter 23 today. We're done with all the points, basically just getting some applications. And then we're going to focus on the exam. I will try to spend no more than half an hour finishing chapter 23 with the example that I have in mind. And then we're going to break into rooms, basically breakout rooms. Regardless of how many we are, we should have about 5 rooms, okay? And the 5 rooms will each room take an assignment, basically going through the review problems. And they should have, each room should have at least 3 problems to look at from the review. And then we reconvene again, we meet again. I will be here, basically moving from room to room while you guys are discussing the problems. And then we reconvene again when we are a whole class again to discuss basically you would have by then walked and solved 3 problems, but you still have 12 more to go from the review, at least the ones that are part of the homework. And then when we meet again, each group basically will discuss the problems that they were assigned to and help the other groups basically prepare their exams, basically go through their entire review for the rest of the problems. You guys understand more or less? I know when we go into it, I'm going to give more clear instructions. Do you guys understand what we're doing today? Okay, very good. So basically that's the plan for today. So you should have your book with you, because you should have I know, and that's another thing also, I know that chapter 23 homework is still not due yet, and which means that you're going to get a head start on it from today, because you're going to be doing it part of the review also. But that's fine. You still have to submit the homework for that chapter later on with all of the problems solved, basically, but after the exam. The focus now is again on the exam that we have beforehand. A very big deal today is that quiz also, which is really intended also to prepare you for the exam too. It is due tonight, so no matter what happened, you have to finish that. That's part of your review process also, and it's graded separately from the actual exam. So it's supposed to be part of a different process, but the whole purpose of this quiz is just to get you ready for the actual exam. Does anybody have any questions so far?
Yes, Professor.
Go ahead.
For the quiz, is it just key points, or are we supposed to do work in the quiz?
There are multiple choice, basically, questions. You're supposed to go through them, and you should have time to go through them and answer them right there on Canvas. You should be graded based on your the options that you have in there. So if you have difficulty with a specific question, please let me know. But I think we're running out of time as far as that, because it's tonight. And it's been available at least for more than a week now or so. Okay?
Yes, Professor.
Okay. So again, for those who are coming late, we're finishing chapter 23, and then we're breaking into rooms, basically. The Zoom will decide which room you're going to be assigned to. And you're going to have a partner or partners during that session working on your room's problems, which are part of the review. You solve the problems together, in which case you have to share your microphone when you are breakout sessions. So you have to at least turn on your microphone, and you can share your screen with your classmates. Basically, you can share, basically, if you work the solution, for example, by hand, you can basically, so, okay, this is the step I did. This is probably wrong. What do you guys think? And they tell you, no, let me show you how I did it. This is, I think, how it's going to work out. By the end of the breakout session, you would have solved 3 problems from the whole review process, okay? Then we come back again. During that process, you're going to, each group basically reports on the problems that they have done, and the rest of the class basically can ask questions or go through the examples or clarifications and things like that. As I said before, I'm not leaving, I'm staying in here. This is what we would have done if we're actually in class. That's how we do the reviews, break into groups. Each group basically work out on some things, and then later on, a representative from the group will show up basically and goes, or the entire group actually goes before the board and explain what they do. That way, we would have had a big, basically, review session leading to the exam. It's still your job individually to actually do the review by yourself, but this session should help you do that. Now, for those who are not live, and I know quite a few of you are not, the breakout sessions are not recorded. That's basically by Zoom's rules, because that involves students, so they're not recorded. So you're going to miss on that. The only thing you're going to do is get back the session when everybody gets together. So that's something that you're going to miss on it. It's still your responsibility too, to go through the process of preparing for the exam by yourself. Okay. Hopefully, these sessions will be helpful for you, and they will be available in time for you to prepare for the exam, which is on Wednesday at 12:45. You're going to be given the class session plus another hour. Basically, I will be available for you guys during that time on Canvas. The session open. So at any time you can jump into the session and ask question. It's a good idea that you actually be logged into the session while you're doing the exam. The reason is because somebody might ask a question and I might answer it and then post the answer on chat session. And if you jump in later in the session, you are not going to see those previously posted chats, okay? So it's a good idea to have your Zoom session open while you're working on your exam. And just before uploading it, that's probably when you want to log out, because to save a little bit of the bandwidth on your end, so that to upload the thing and you're done with it, and then you can go somewhere else, okay? So that's the whole process for this week. This week is focused on the exam. Everything else can wait. Everything else can be done later, because the exam has a very high weight and it has to really be done right. Okay? Does this sound like it's a good plan to everybody? Yes? Okay, very good. So let's first of all get chapter 23 out of the way. I mean, we did it, but I just want to make sure that you guys are, we got at least a couple of examples that we have. Where is the share? Here is the share. Okay, so hopefully you guys are looking into my OneNote. And just to make sure, basically, there are some key concepts in here for the potential that we have so far discovered. That the electric field, where is my pen? Here. That the electric field derives of a potential just as much as the force derives of a potential. And what that means is that, okay, I'm not drawing. What that means is E symbolically is equal as minus a grad of some scalar thing, or some scalar function, okay, V. Just as much as when we did physics for A, we said that the force derives. I know we didn't. We did it only in 1D. The focus was in 1D in physics for A. Only when you dealt with rotation, when you introduced more than 1D, really. But even then, it was a minus the derivative with respect to x of some scalar function, which later on turned out to be the potential energy. So that's how we're usually symbolically we write it, where U in this case is the potential energy. And this is the electrical potential. Okay, somebody asks, okay, what's the difference between them? It's Q, okay? That's basically what the difference between these two things are. In other words, U is equal to QV. You have to understand, because of the fact that the U itself is the integral of the force, or V is the integral of the electric field, V is equal to minus the integral of EdL. This is still a scalar. This is still a scalar function. But as you know from your calc classes, that an integral is defined within a constant. So what matters really is the potential difference, delta V. Delta V is some potential difference between 2 points, okay, A and B, EdL. Because of the properties of this integral, it's actually the integral from B to A of dl. Okay, the point being in here is just to reverse the sign for this one. The minus, as I said before, and you guys probably have discussed this one in physics 4a, was introduced just for cosmetic reasons, so that you can say that the total mechanical energy of a system, the total mechanical energy of the system, it's a scalar, is equal to the kinetic energy plus potential energy. And that's what you probably have seen. Maybe you've used different symbols for the kinetic and potential, but that's basically what that means. Otherwise, it's going to be minus something in there, okay? So the minus was introduced part of the definition of the energy, and that's potential energy, and that's basically how this thing you guys have had it. So this is in a nutshell what we did. For the electric field, the only thing we did actually was to prove that the electrostatic force derives of a potential. Basically, we find the integral, because there is another definition that you will see it later on, that actually from calculus 2, that any vector function can derive from a potential if its curl is equal to 0, actually. And since we didn't deal with the curl yet, and we're going to need it down the road in 2 or 3 chapters from now, we're going to defer that discussion to later on. And just basically, we found what this potential is. We're just doing the integral, that's all. The integral of negative 1 over r squared was 1 over r for a point charge, and we generalize using the superposition principle. So this is in a nutshell everything we did so far. And there was actually something we did actually toward the end, and namely that the equipotential was defined so that there is no, we are on a surface where there is, in every point on the surface, the potential is the same. So when I calculate the difference in potential between 2 points on the surface is going to be 0 no matter which these 2 points are. They're close or far. That is what the definition of equipotential means. Practically, you can trace it. You can, if you find 7 volt, you can with a multimeter find another 7 volt. And if you map that region, that is your equipotential, okay? So that's basically what the equipotential is. There is no difference in potential between any 2 points on the surface. When we went back to the integral, we saw that this integral then vanishes anywhere on the surface. And that can only be true if the integrand is 0. If the integrand is 0, that means that what you're integrating is 0. This dot product must be 0. Since we avoid the trivial condition where the electric field is 0, that is actually an equipotential too, we're going to have it in general true if these 2 vectors are perpendicular to one another. In other words, the electric field is always perpendicular to the equipotential, because this dl has to be on the equipotential surface itself. Since dl and E are perpendicular, that means that the equipotential is always perpendicular to the equipotential surface. So this is basically in a nutshell what we did on Wednesday. There were some key concepts that we needed to get out of the way. For example, the electric potential. Since we know it, since we know that the derivative of the potential, or the integral of the the path integral of the electric field is actually what that potential is, we could carry the integral wherever we want to. The difficulty usually arises from the fact that we're dealing with multi-dimensions, and that's why the curl, that's why the gradient operator was introduced, because if we could have simplified the problem into 1D, we would have done it using just a regular derivative. But because this is a more than 1D problem, we have to really deal with that issue. There are a few cases where it's simple enough to do the problem. Let's say, for example, this is one of the applications, take 2 plates. One of them has distribution charge of sigma, the other one distribution surface charge of negative sigma, and we saw that these 2 plates are what we call condensers, and we're going to see them in next chapter with full-fledged, that the electric field in here is 0, the electric field in here is 0, and the electric field in here is simply sigma over epsilon naught, pointing downward from the positive plate to the negative plate. So we saw this one. It would be interesting in this case to try to find what the potential difference in here. This is a case where we can do the integral very, very easily. Let's look at it. Let's call this one the y-axis. Okay? If this is the y-axis, positive pointing upward, it's clear that the electric field is pointing downward, it's negative electric field. So the electric field in this vector representation should be then E equals to, as a vector, minus E minus sigma, if you like, sigma over 2 epsilon naught. I'm sorry, 2. What is 2? It's epsilon naught times j hat, where j hat is this direction. Okay? So basically that is as a vector, okay? Now, if we do the dot product, so this is how much dy now is. dy is, dl, if you wish, is dy times j hat. So j hat times j hat is going to be 1, and the negative is going to work out itself so that the dot product of edl will be simply equal to minus sigma over epsilon naught times dy. Okay? Does everybody see where the minus is coming from? The minus is coming from the fact that the electric field is pointing downward and the axis is pointing upward, so EDL is a negative number. So now if I want to find to integrate from the negative plate to the positive plate, or from the entire area, so this is how much the electric potential is going to be. So I'm going to start from the lower plate, okay, at some point y of integrating minus EDL. So there is a minus and a minus, it becomes positive. So the integral simply becomes positive from the lower plate to somewhere y between the plates, okay, of sigma over epsilon naught dy. And this is a very simple integral in this case. It's just sigma over epsilon naught y, okay? So that's what the potential difference in here at some point y. So delta V must be equal to sigma over epsilon naught evaluated from the lower plate. That means I'm going to take it as the origin. That means that's where y is equal to 0. So which means that times y. In other words, if the separation between the plates is actually d, at the upper plate, the potential will be sigma over epsilon naught times d. So the V upper, or the V upper, minus the V lower is simply sigma over epsilon naught times the separation of the plates, how separated they are. Anywhere in between them, it's just how high I'm going to go. This is just, if you guys, reminds you of the problem with gravity. If you go distance h, you're going to gain mgh. So if you go high a meter, you're going to get mg times 1 meter. That is a potential energy. This is exactly similar. This looks mathematically, if we replace sigma over epsilon naught by mg, this is exactly, but of course we have to multiply this whole thing by q to make it into joules. Q times sigma over epsilon naught. Q in this case is m, the mass. So this looks like g times the height. Okay? This looks exactly like what you did, guys, in physics 1A. Namely, if I take a positive charge in here, positive q, and let go of it, it's going to fall and accelerate just like you have a free fall. The only trouble with this situation in here is if I have a negative charge, negative q, then actually it's going to fall up. Okay? Whereas a positive charge is going to fall down. That's the only difference. Because in real life, we don't have negative masses. If we have negative masses, the negative masses will fall to the ceiling, whereas the positive masses will fall to the ground. So that's the only difference between that and this problem. Between the problem from physics A for A and for the problem from physics 4B. Is that in this situation, because you have positive and negative charges, you have the possibility that some of them will fall to the positive plate and some of them will fall to the negative plate. Whereas in day-to-day experience, since nobody discovered negative masses, all the masses fall to the ground with the acceleration g. Whereas in this case, they fall to the ground, to the lower plate with an acceleration of sigma over epsilon naught. Not acceleration, with g, that is equal sigma over epsilon naught, if they are divided by times q divided by their mass, if we really want to have a meter per second per second. But the point being in here, this is the field that drops them down. Okay, if they're negative masses, they're going to fall to the ceiling. Now, if somebody tomorrow discovers, and probably there is some theories about it, that there are negative masses, this negative masses probably have escaped to the other end of the universe because of this reason, because of the force of gravity is doing them somewhere. But at least from our daily experience, this is what we see. So this is an important application. I think it's one of the homework problems that you're dealing with the electron shot through between the two plates, and then it's going to follow a projectile path, basically. And that is how the cathodic tube. I don't remember which problem is that, but that's one of your review problems actually from this chapter. So this is one of the applications that I thought, and it's important because actually we're going to need this stuff down the road. We're going to need it in next chapter actually. And there are a couple of more applications that I want to bring to your attention. And that is going to also be needed next time around when we meet from chapter 24. And that is the so-called coaxial cables. But before we do coaxial cables, we're going to talk about a long rod of charge distribution lambda. Okay, when we calculated the electric field, we found the electric field to be equal to lambda divided by 2 pi times epsilon naught divided by the distance, r, where r is where the point we're trying to find the electric field in it. It's pointing upward, okay, from that chart. Again, I want to find what the potential is in this case. We do the same thing. We follow the same steps as before. So we're doing here in this case E times dr. So dr in this case is pointing upward, and the electric field is pointing upward. So the dot product is actually going to be positive. But don't forget, in the definition of the electric field, they have a negative sign. So that means I have delta V, the difference in potential from some starting point, which we have to be very careful with in this problem, and that's the reason of this exercise actually. We have to be negative from some starting point, which I'm going to call A, to some final point, which we're going to call B, which is has a definition of R anywhere in the space outside of the wire, is equal to E times dr in this case, okay? Again, it's a one-dimensional single integral because everything else resolves. There is no X and Y directions. It's only the direction away from the wire that matters. So in this case, we will end up with an ln because dr over r is going to be a logarithm. So delta V is equal to minus lambda over 2 pi epsilon naught, I sub the value of E, by the way, times the integral from some starting point to some point, which I'm going to call a position R, of dr over r. And the integral of dr over r involves the log, okay, the natural log in this case. So we're going to have that, which brings me to the point of where, because again, we're saying that the electric potential is defined within a constant, so I have to be very careful with our choice of the constant. So the difference in here is going to be negative lambda over 2 pi epsilon naught ln of r evaluated between some starting point and some point A and some r, okay? I cannot choose A to be 0. I cannot choose the starting potential to be right on the wire itself, because if I do, ln of 0 is infinite value. I cannot say, like we did with the point charge, that I'm bringing it from infinity when it was not interacting, therefore there was no potential there. I cannot say the origin of the potential is at infinity either, because the ln of infinity is going to be also infinite. So in this case, this potential blows up in both ends. So we have to define a point where it is suitable for us to call that potential to be 0, and from there on, we calculate the potential. Is it more or less? Okay. So if we define the potential in here, in other words, where you put the ground, we're going to go practically, you're asking me, what is that supposed to mean in practice? Where do you put the ground? Because a multimeter has two ends. One is ground, and one is actually the probe that you find the difference in potential between the ground and where you're measuring. So that is the thing in there. So ground that point, that is your starting point. Any point with a higher value, positive value, is actually on the positive end. It has a higher potential. Anything with a negative value, it's a lower potential. That's basically what that means in terms of practice. We have a choice in the case of the point charge to choose the ground at infinity. So we had a value anywhere in there, but it's still true even in that case that we're finding the difference in potential, because you really have to define it with that constant too. in the previous example, we took the starting point, the lower plate, to be our potential V equal to 0. So we grounded that point. Okay. Anything else in here in this case is going to be a finite value. So if we find 12 volt in here, what we're saying actually is this 12 volt is with respect to this point. So if this one was 1,000 volt, the other one is 1,000 plus 12. That's exactly what's going on in your wall also at home. It says 110 volt. It really is talking about the difference between the two ends. That's all. So one of them could be 100 volt, and the other one is 100 plus 120 volt to 220 volt. One of them could be 723. The other one is 723 plus 120. Basically, what matters in this case is the difference of potential. Same thing in here. So somebody asks, okay, what is the potential in here? It's going to be 12 volt because this is a constant. The integral of a constant is constant. So in this case, it should be the same constant all the way through. And in here, it's going to be 0. Integral of 0 actually is a constant. I'm sorry. So this is some of the points. When we come to the coaxial cable, though, you will see what matters is actually the difference in potential, because coaxial cable is made up of two cables, basically, two cylinders, one inner and one outer. Okay, so what matters in there is the difference in potential between the inner part and the outer part. Okay, so in the log in there, it should be the log of the ratio of the radii. Okay, R interior divided by R exterior, or vice versa. The point is the ratios, because when you take the difference in the log, you're going to end up with the. So that's a second example I wanted to bring to your attention to. And I know we're approaching the half an hour, because I told you we should only take about half an hour for this one, unless you guys have a question about this stuff. Okay, one final point in here that yeah, the disk, which is important, the ring also, because at some point we need to deal with the ring too. I think it's one of the homework problems also. A ring is very simple calculation, because when we do the calculation for the so I have a ring in here. So this is a circular shape that I tilted a little bit, and I want to find how much is the potential somewhere in there, V in that point. The ring has some sort of linear distribution, which I'm going to call lambda, which is a charge divided by the whole thing. In this case, if I take this distance and integrate through the entire charge dq in the ring in here, and this ring has a radius r, and we are at some point x on the x-axis. So the point in here, this integration is very straightforward. It's easy, kind of easy. So it's going to be for the potential, which is, I'm going to ignore the sign right now, but you're going to restore it later on. So I'm going to just find the entire derivative of E dl. Since I don't have to deal with the, and dl in this case is going to be basically this displacement, okay? Again, we're going to integrate, and the electric field integrated through that distance, it doesn't change, okay? So basically, or take a dq in this case and assume it to be your charge. So dq will produce an electric field, electric potential dV, which is equal to, for a point charge, we already found it to be dq over 4 pi epsilon naught times the distance. And the distance in this case is the square root of r squared plus x squared. Okay, that is the Pythagorean theorem. So if we plug into that expression for the volume, for the element of charge dq, and since the distance doesn't change in this situation when we are on the ring, when we move throughout the ring, then this integration just becomes of q. And the potential in this case is going to be the q charge oops, what happened in here? The q charge divided by 4 pi epsilon naught times the square root of r squared plus x squared. Basically, when you integrate through a ring, all you're carrying with you is just the charge throughout, okay? Because the distance between every single element, dq, this element, as it moves throughout the ring, the distance between it and where we're trying to find that the potential is the same. It's always square root of r squared plus x squared. Since r of the ring doesn't change, and the point where we're trying to find the potential doesn't change, so the distance between every single element of the ring and where we want to find it doesn't change when we sum through the potential using the superposition, since we can find it for a point charge, and this is how much it is for a point charge. dq over 4 pi epsilon naught divided by the square root. So you just sum through the other problem. I think there is a homework problem also that takes advantage of this thing in here when we're talking now about actually a cylinder with some charge distribution on it's a hollow cylinder, and you want to find the potential inside of it. And the cylinder, whether a finite or an infinite, then you have to sum this quantity throughout. You have to add the contribution from both ends, all ends of the cylinder throughout. So consider the cylinder as it's made up of an infinite number of rings, basically. Okay? Since the radii doesn't change, the only thing that matters then is that since I move from one ring to another ring on the cylinder, this distance starts to change on me, so I have to really sum during that point. This one you don't have to. So this is some of the points that I wanted to share with you guys as far as the review, as far as the applications for this chapter. And barring any questions, we can start on our activity, and I'll give you exactly what is it. Any questions for this applications? Please do more applications from the book, okay? That is, I know in the instructions, they tell you which examples you're supposed to be doing. Please do all of those examples, go through them. They are solved in the book. If you have any questions about them, please let me know. Any questions before we break into our sessions? No? Okay. Let me explain the process again. You have 5 problems from each chapter. They are your homework problems, okay? We're going to break into 5 groups, basically, in this session, breakout sessions, okay, breakout rooms. Each group will handle the number of that they're assigned to. For example, if I'm in group 1, I'll go to homework number 1 and pick up problem number 1. I go to homework number 2 and pick up problem number 1. I go to homework number 3 and pick up problem number 1. Do you guys understand that? If I'm in group 4, for example, then I go to homework number 1 and pick up problem number 4. Homework 2 and pick up problem number 4, and homework 3 and pick up number 4. Is this clear now? Which group has what to do? Okay. So again, I'm going to put it in here. Each group will pick up 3 problems, 1 from each chapter per their room number. So again, Zoom is going to tell you what your room is. So if you land on group, for example, 5, room 5, you know that you have the 5th problem from each one of these chapters. If you land on the 2nd room, you're supposed to pick up only the 2nd problem from each one of those. So you'll end up with 3 problems. Then you turn on your, first of all, you're going to receive an invitation from Zoom. Please accept it. And if by mistake you don't accept it and you're bumped out, come back. I will be here in the general session and I can send you to where you're supposed to be, okay? Back again, okay? Then once you go into your breakout sessions, please turn on your microphone so that the other person or the other 2 people who are working with you, they can basically work with you. They can hear you and you can hear them and you can work together, okay? Now, once you are there, once you turn on your microphone, at that point you have the problems, you know exactly what problems you're supposed to be working on. And I will come in and make sure that you guys are working on these things. And if you have any questions for me, and if you want clarifications about the process. Now, like I said, you can work on your screen and share your screen, or use your camera to share your work with your classmates. Basically, this is what I think the solution is. And you are free to use whatever resources you have. So if you have an online source or if you have a solution manual somewhere, that's the time when to pull it, okay? The bottom line is you need to have a full understanding of what the solutions are. You need to understand exactly what the problem is. So you need to know all of the details about the problem. So if somebody later on tricks you and gives you a completely reversed version of it or completely messed up version of it that doesn't look anywhere near it, but at the end, those insights should be very helpful for you in basically cruising through the exam. Yes? Does the instruction sound correct now? Okay, so we have 18 people, 19 counting me. So we should be really about 3 people, sometimes more per session. Okay. So the rooms are gonna be 1, 2, 3, 5, 3 to 4 participants per room. Okay, create rooms.